Okay, so this is Math2240. I am Dr. Amsamuj, and this is the uh, Myelearning website for Math2240 Engineering Stats. Okay, so on this Myelearning page, there's links to a couple websites with material, right? So my Math2240 website is this site over here, right? So you can just click the link, of course, and get to this site, right? Okay, so on this website here, there's course notes available for the course, right? So this is what the course notes would look like over here, right? Course notes are available using this link, right? Your lecture schedule is Monday 5 to 6 and Wednesday 1 to 3. You have lectures then, right? And then you have a tutorial on Friday 5 to 6. Right, so the course consists of probability and statistics. So your major topics here, these 7 major topics, they would be split into probability here and statistics, right? So your first 4 topics, probability, random variables, expectation, discrete and continuous probability distributions. These are probability topics. And then your remaining 3 major topics here, the sampling distributions, the hypothesis testing, the linear regression and the correlation. These are stats topics. Okay, you need a knowledge of your probability to do your statistics questions, right? Okay, right. The course textbooks, well, course texts more for reference because really these course notes are very detailed, right? Detailed to a certain extent where some of, say, like the props so you may not need in the course, but we will explain that as we move along, right? So what I'm saying here is that really you could really just work with the course notes in terms of a reference, right? But if you want additional references, you can look on my website here, right? And there's some textbooks available, right? Okay, so for example, there's the decking, which is you can get, you can download from UE Library. There's Kearns, which the PDF is available here, right? Okay, so this reference here, Walpole, right? The course notes here are actually based on Walpole 9th edition, right? So these section headings, right, actually correspond to the section headings in Walpole, right? Walpole is not freely available, right? You can probably borrow a copy from the library or you obtain a copy otherwise, right? Right. There's also this site here, which is a website which basically is a probability and statistics textbook, right? It has embedded exercises and so in it, right? We're not going to cover everything in this website, obviously, right? Okay, and additionally, there's some Scan 2240 notes that probably a little bit on the old side. You can look at this for additional reference, but as I said, your main reference would be either my course notes, which would be these course notes over here, or Miss Bhutan's course notes. Right, so your assessment structure for Math2240 would be very similar to what it was for Math2230, right? You're going to have 3 coursework exams, each one with 30%, right? And then you're going to have 4 assignments, each with 2.5%, right? So that would sum to 100% here, right? The structure of these coursework exams, right? How they implemented would be, these would be, you do them on Myelearning, similar to the structure of what you did for 2230, right? So in particular, you're gonna have 12 hours to do them, right? And there would be questions of a similar format as what you saw in 2230. The assignments will also have a similar structure, right, to what the assignments in 2230, right? So in particular, your assignments would be, you'd have 4 days to do your assignments, okay? Okay, so this website has practice questions and solutions, right, that you can use, well, to practice, right? All right, okay, so let's start the course material, right? So we're starting with probability, right? So first thing we want to talk about is an experiment, right? Okay, so an experiment is any process that generates data, right? We can distinguish between 2 types of experiments. You have deterministic experiments and random experiments, right? A deterministic experiment is an experiment where you can actually predict the outcome beforehand, right? So for example, if you do an experiment when you mix in, say, like hydrogen and oxygen, well, then you expect to get water, right? Or if you consider in, say, a mass spring system. Okay, so if you consider in a mass spring system, the displacement of your mass from your equilibrium position would be modeled by a differential equation such as this. This is assuming that there's no damping, right? And in which case you can actually deterministically figure out what your displacement is going to be at any time t, right? So there's no probability or no chance associated to this, right? If you want, this is, well, it's a predetermined response that you can actually figure out what displacement. You can predict with certainty what your displacement is going to be at any time t, right? Okay, so deterministic experiment, the outcome of your experiment, you can actually predict using some sort of theory to derive your result beforehand. Okay, but on the other hand, a random experiment is where you wouldn't be able to predict the outcome of your experiment beforehand, right? So the outcome of your experiment is determined somehow by chance, right? Okay, so an example of a random experiment is, for example, if you roll a die, right? So this software over here is giving you a little simulation as if you roll a die, right? So if you roll it, you can get, say, 2. You can get 6, right? So this is supposedly randomly rolling it for you, right? And when you roll a die, each time you roll a die, you can get different outcomes, right? But you can't tell beforehand what the outcome is going to be, right? What you can tell, however, is what all the possible outcomes can be, right? And that's something we're going to use in this course, right? So the set of all possible outcomes of an experiment would be called your sample space, right? We will define that in a little while, right? So you set of possible outcomes when you roll a standard die over here, right, is you have 6 possible outcomes, right? So you're going to have, when you have 1 dot, say 2 dots, 3 dots, 4 dots, 5 dots, and 6 dots, okay? Okay, so a set of possible outcomes would be basically 1 to 6 here, right? For when you roll a die, when you roll a single die, right? Okay, so other possible random experiments, if you say you flip a coin, right? Well, if you flip a coin, you're going to get either heads or tails, right? But before you flip, you can't really tell what the outcome is going to be, right? So that the outcome of tossing a coin is that's a random experiment, right? Because you can't determine what the outcome is beforehand, right? Okay, if a next example of a random experiment is, suppose you're driving home, right? And if you're driving home, you can count how many red lights you encounter at the various intersections that you go through, right? and number of red lights that you would go through, right? That's in fact, to some extent, it's it's random, right? Or practically, it's random, right? So if one day when you're driving home, you probably get, say, encounter 2 red lights. Next day when you driving home, you could probably encounter, say, uh, uh, 5 red lights, right? Obviously, there's going to be a range of red lights that you would encounter because there's only so many intersections that you'll be passing through on your normal way home, right? So this the set of numbers of red lights over here that you would encounter, right? That would you'd be able to actually list all the set of possible outcomes for this random experiment, right? So because this is a course on probability, your experiments in this course is all the experiments are considered to be random experiments, right? Okay, so here we have this definition, which is particularly important for us, right? Especially in the beginning section of this course when we start to talk about probability and calculating probabilities. All right, so your set of possible outcomes of interest for an experiment is called the sample space of an experiment, right? And it's denoted by capital letter S over here, right? Okay, so for example, if we toss in one dice, right? One die, right? Then the set of possible outcomes would be 1 to 6 here, right? And you see in it as we saw here, right? Your set of possible outcomes could be 1 to 6, right? And by 1 to 6, it means that you're really just counting the number of dots that's showing up on the top face for your die, right? Okay, so your sample space for this experiment for tossing one die once, right? This is your sample space. Your sample space consists of all your possible outcomes, and those would be the numbers 1 to 6, right? So consider a different experiment in this case where we flipping a coin, right? And we're letting it land, right? And we're observing if we get a head or a tail, right? Okay, so what do you well, remember what sample space is supposed to be, right? Sample space is supposed to be the set of all possible outcomes of the experiment, right? So this experiment of flipping a coin, right? Well, what are all possible outcomes, right? Well, all possible outcomes would be either head or tail, right? So we use just a little bit of shorthand notation. The H will denote head and the T will denote tail, right? Okay, so one thing you want to notice here is that sample space is set of possible outcomes, right? So what we're going to do is we're going to be a little formal here, and we're going to use set notation to indicate that that this S is going to be a set, right? So if you write in your possible outcomes over here, you want to enclose them in these curly brackets to indicate that it is actually a set here, right? Okay, and this sort of set notation again is fairly important for us because we're going to be using sets for the first couple sections of this course. Okay, so let's notice something in this definition here, right? So sample space is set of all possible outcomes of an experiment, right? But I have this in brackets here of interest, right? So it's if you have an experiment, right, you can have different things that different sort of outcomes that you're interested in the experiment, right? So for a simple example of this, let's go back to the case where we roll in one die, right? Okay, so if you're interested in number that shows on the top face, right, then your possible outcomes would be 1 to 6, right? So that would be a sample space, right? But if, however, you're just interested in that number that you get, right, whether it's even or odd, right, and if that's all you really care about, right, then your sample space would be either even or odd, right? Okay, so notice it's really the same experiment that you're doing, right? Tossing one die, right? But your sample space would be different based on what you're interested in, right? Okay, okay. I mean, this is somewhat something of a fine point, right? But remember, if you're doing say complicated experiments and so on, right? You may be interested in different uh, observing different types of variables and so, right? Okay, so if you observe one type of variable, you'd get a certain sample space for that. And if you observe a second type of variable, you get a different sample space for that, right? So the point that I'm making over here is that your sample space depends on what you're interested in the experiment. Okay, so let's look at a somewhat more complicated example. We have a coin, but we're gonna toss it 3 times, right? So what you're gonna do is you toss it once, you record the observation, right? Then you toss it again, you record that second observation, and then you toss it a third time and record the third observation, right? Okay, so what we want to get is we want to get this sample space, right? So we want to get possible outcomes that would occur that if we toss the coin 3 times in sequence, recording the result after each toss, right? Okay, so in this case here, if we actually wanted to list out all the experiments well, they did ask us to find the sample space, so we need to enumerate the elements in the sample space, right? Okay, so, well, one way to do this is by using a tree diagram, right? So this tree diagram here, what this is supposed to indicate, this is this point over here, right? This is supposed to indicate that you start any experiment, right? And these are your possible outcomes after your first toss, right? So you can get a head or you can get a tail, right? Okay, now let's suppose we got a head on the first toss, right? Then what we do is we need to remember we're going to be tossing this 2 more times, right? So when we toss it the second time, we can get 2 possible outcomes, right? Which is head or tail, right? Okay, so let's suppose we had a head, and then the second time we did the experiment, we got a head, right? Second time we tossed the coin, we got the head, right? And then the third time we toss the coin, we now get a tail, right? Okay, so that outcome in that case would be head, head, and tail, right? Which would be this one here, right? Head, head, tail, right? Okay, and notice here what I'm doing is by this tree diagram here, I'm able to see what all the possible outcomes are going to be, right? So if it's head over here, right, in the first toss, then you can get, and you toss it again, you can get on the second toss either head or tail. And then for each of these again, on the third toss, you can either get a head or a tail, right? Okay, so to get all your possible outcomes, you just really you start in over here, and you really want to get to this end point over here, this end node over here, right? So to get, and because this is a tree, there'd only be one way to go from this start over here to this end here, right? So go in, if I have this H over here, the only way to go from there to there is head, 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 right? So that gives me this head, 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 right? And if I have this tail over here, the only way to get to this is head, head, tail, right? Which gives me this outcome. And likewise, say for this tail over here, this one down there, right? The only way to get to that is head, tail, tail, right? So that outcome would be head, tail, tail, right? Okay, and you want to notice you can actually count the amount of possible outcomes that you're going to have. You have 8 possible outcomes over here, right? So your sample space is, you have 8 elements in your sample space, and these are actually, each of these triples over here is an outcome in your sample space. So your set of your sample space is a set of all possible outcomes, and that would be 8 of these over here. Now, when you're writing them, you want to be a little formal and write them as a set, right? So required sample space, you just take in these 8 over here and writing them together in set notation. Alright, so let's again consider the experiment of rolling one die, right? A single die, right? So your set of possible outcomes, which is the sample space, would be, as you saw, would be 1 to 6, right? Okay, now what we're interested in is a certain event, right, occurring in the experiment, right? And the event is that the outcome that you get is divisible by 3, right? Okay, so how can you describe that event, right? Well, how you describe that event is by listing all the outcomes in your sample space that satisfy this criteria that the outcome is divisible by 3, right? Okay, so listing those, it would be the 3 and the 6, right? Okay, so your event that the outcome is divisible by 3 is in fact described by this subset over here, 3, 6, of the large sample space, which is 1 to 6 here, right? Okay, all right, so event that the outcome is divisible by 3, event is, first of all, is really just a subset of your sample space for experiment, right? And more generally, any event, that is what an event is, right? So an event is really just going to be a subset of a sample space, right? Okay, so let's just look at, say, these over here, right? So B, my sample space is this S over here, 1 to 6, right? Which is the same S here, right? And I'm considering these events now, 1, 2, 3, and 1, 2, 5, right? Okay, so this here is a subset of my sample space, right? So this is an event, right? The event has a nice description, right? Because you can describe it as all your outcomes that are less than or equal to 3, right? Okay, so this is an event that has a nice description, right? This is the event of obtaining a value less than or equal to 3, right? When you roll the die, right? Okay, but how about this over here, right? This 1, 2, 5 here. This again is a subset of your sample space, which is this S here, right? Okay, this here, it is an event, right? Because by definition, it's a subset of your sample space. But this one doesn't really have a nice description, right? 1, 2, 5. It's probably hard to cook up a nice description as the B over here having this nice description, right? But that doesn't prevent it from being a subset of your sample space, right? And therefore it is an event, right? So the point that I want to make is that if you have a sample space, any subset of it, right? So this is a sample space, an example of a sample space. Any subset of it is an event, right? Some events have nice descriptions, like this B over here and this A over here, but some of them don't have nice descriptions, but they're still all just events, right? Right, so let's do our next example of obtaining an event, right? Okay, so I have an experiment where we toss a coin 3 times, right? What we want to get is the event of obtaining heads exactly twice, right? Of tossing heads exactly twice. Okay, so the sample space for this experiment we found already, right? We found by using our tree diagram, and this is the sample space of my experiment. Notice that you have 8 possible outcomes over here, right? And what we want is we want the event of obtaining heads exactly twice, right? And that's not hard to do. All you need to do is you just need to look among these 8 outcomes and just choose the ones where you get a head exactly twice, right? And that would be these 3 over here, right? Okay, so this is the required event, right? This is the event of obtaining heads exactly twice, right? Okay, so we got that from the sample space, and next way to do this is, well, if you're going to get a head exactly, if you're looking at outcomes where you have a head exactly twice, right, it means that you're going to have exactly 1 tail, right? And that tail could either be in the first position, second position, or third position, right? So you see, for this particular problem, you don't really actually need the sample space to get the event, right? You can actually reason out what the event is by just using the information from the problem. Right, so because your sample space, for example, is a set here, right, and the events are in fact subsets of this sample space, this big set here, right, also called a universal set, right? Okay, what we could do is we can use, because your events and your sample space are actually just sets, right? What we do is we can actually use normal set operations for events and for sample spaces, right? Okay, and what do I mean by normal set operations? I mean things like, for example, intersection, right? Okay, so if I have two events A and B, right? So for example, here two events A and B, right? That events are subsets of a sample space S over here, right? So your rectangular box over here is indicating the sample space, right? Okay, so set of possible outcomes. And then the events A and B are just subsets of your sample space, right? So this is a normal Venn diagram, which I'm quite sure that you saw already, right? Okay, and diagrammatically, the intersection of A and B, right? If you have A over here and you have B over here, intersection of A and B consists of all the elements that are in common with that belong to both A and B, right? So that is what this says over here, right? Okay, and also you have union. So again, sample space S, you have two events A and B, right? And what the A union B is, it consists of all elements that belong to either A or belong to B, right? Or it could belong to both of them, right? So notice A union B is different from A intersect B, right? A intersect B consists of elements that must belong to both of them, right? Must belong to A and must belong to B, right? A union B means it can belong to A, belong to B, right? Or it could belong to both A and B, right? All right. So that's what A intersect B is, what A union B is, and then we have. Okay, so if we have our sample space and we consider a subset that doesn't contain any elements, then that subset is called the empty set and is denoted by this phi over here, right? Okay, this empty set is with reference to the big sample space S over here, right? Okay, so I mean, can't really diagrammatically indicate an empty set like the A and the B, right? But you can get an idea what it is from, say, this picture here, right? So what I have is this represents A over here, and this represents B over here. And the fact that these circles are disjoint indicates that there's no elements in common with A and B, right? Which means that A intersect B has no elements. There's no elements in common with A and B. So the intersection of A and B is empty. And the intersection of A and B is a subset which contains no elements, and therefore it's the empty set here, right? So if you want, this is one way to see what the empty set is, right? You have A and B which have no elements in common, and the intersection is the empty set. Okay, and something we also need to know is what the complement of an event is, right? Okay, so I have sample space S here, right? So the sample space S here is indicated by this square set here, right? And I want the complement of an event A, right? Now the event A is a subset of your sample space, so this is this reddish pinkish set over here, right? And your complement of A would be all the elements that are in S that do not belong to A, right? So if you want everything outside of this subset A over here, right? In this diagram, they use the notation A with a small c over here to indicate complement. But in this class, how we're going to indicate complement is A prime, right? So the prime over here indicates A prime indicates that it's the complement of your event A. Alright, so here are some basic examples of using the above definition of union, intersection, and complement, right? Okay, so the sample space is this set S over here, which is 0 to 9, right? And the events are A, B, C, and D, right? And you want to notice the A, B, C, and D are all subsets of this S here, right? Okay, and question asks you to get A union C, right? So it's A union C consists of all elements that either belong to A and C, right? So you want to notice that, well, I have 0, 2, 4, 6, and 8. I also have the 2 and 4 over here. And so to get A union C, I'm not going to repeat the 2 and the 4. I'd have 0, 2, 4, 6, and 8, and then the 3 and the 5 as well, right? So which is this over here, right? Okay, A intersect B are elements in common with A and B, right? What you want to notice in this case is that the A over here actually consists of just even numbers, right? So it's subset of S that would be consists of all even numbers. Okay, so A is all even numbers of S and B are all odd numbers of S, yeah, right? And A and B have no elements in common, so the intersection is the empty set, right? Complement of C in S, right? So C is 2, 3, 4, 5, right? So, and complement of C would be all elements in S that do not belong to C. So you take the S over here and you take out the C, right? And the C is 2, 3, 4, and 5. So when you take out the 2, 3, 4, and 5, you get 0, 1, 6, 7, 8, and 9, which is this here, right? Right. C complement intersect. Let's work out this one over here. This is a little more interesting. Notice the use of the brackets here, right? So the use of the brackets here means that you need to work out this intersection here first, right? And then take the union with B, right? Okay, so we need C complement intersect D, right? Well, I already worked out what C complement is, right? So C complement is 0, 1, 6, 7, 8, and 9, and the D is 1, 6, and 7. Okay, so first thing I need to do is need to take the intersection of those. I get intersection of these two would be 1, 6, and 7. And then I take the union with B, and B is 1, 3, 5, 7, and 9. Alright, so when I form the union, the only thing additional that this set over here contributes to this is the 6. So I get 1, 3, 5, 6, 7, and 9. Right? Okay, so this last one over here, S intersects C, right? Complement, right? But C is actually a subset of S, right? So if I take the intersection of C with S, I'm just going to get back C itself, right? So S intersects C is actually just equal to C, right? And then all I need to do now is just take the complement of C. And the complement of C I worked out already, which is this here. Right, and here we have this definition that two events A and B of a sample space mutually exclusive, or also called disjoint, right? If the intersection of the events is the empty set, right? So remember, the A and B events are just subsets of a sample space, right? So those subsets are said to be mutually exclusive or disjoint if the intersection of the subsets is the empty set. Right, so let's see an example of that, right? We have an experiment where we draw in one card from a standard deck, right? So remember, your standard deck is 52 cards, 13 cards in each suit, and you have 4 suits, right? Okay, so A is the event of drawing a king, and B is the event of drawing an ace, right? So, well, what is this event A, right, of drawing a king, right? Well, the event of drawing a king, this is a certain subset of your sample space. So this is the subset. This is the possible outcomes of your sample space that satisfies this condition of drawing a king, right? So in other words, it's all possible ways of drawing a king. And all possible, you have 4 ways of drawing a king if you pull in one card from a deck, right? So you can get the king of hearts, king of diamonds, king of spades, or this king of clubs, right? So this here, this is the event of drawing a king, right? When the experiment is pulling one card from the deck, right? Okay, and likewise, the event of drawing an ace is, well, you can either, the possible outcomes in this event is you can get an ace of hearts, ace of diamonds, ace of spades, or ace of clubs, right? Okay, so notice that both of these subsets of your sample space, and the sample space is in fact if you write out the sample space S, the sample space S is a set of all 52 cards, right? Anyway, so I have, this is event A, which is drawing a king, and this is event B of drawing an ace, right? And what you want to notice is that these sets over here, right, so these subsets A and B have no elements in common, right? So the intersection of A and B are going to be empty, right? So this is an example of two disjoint events. Okay, so let's take a look at some properties of events of a sample space, right? Okay, so I have these over here, right? And to see these or to justify these, it's useful to some of them you can show them using Venn diagrams, right? So for example, this one over here, right, where A intersect A complement is the empty set, right? If you consider this Venn diagram over here, subset A is represented by this uh, circle over here, right, which is shaded blue here, right? Okay, so this is A here, and A complement would be all elements that belong to S that do not belong to A, right? So the A complement would be your green shaded area over here, right? And the S, of course, is represented by what's inside this rectangle, right? Okay, and you want to notice, if you're looking at this Venn diagram, that you have no elements in common between A and A complement, right? So the intersection of A and A complement is in fact the empty set, right? Okay, and using the same diagram, you want to notice is that if I consider the union of A and A complement, so this is A over here, and I take the union with A complement, what I get is I get all possible elements in a set S, right? So the union of A with A complement just gives me back the S, which is this here, right? Okay, likewise I can in fact show this one over here that A complement is equal to A, or at least justify this statement here using this Venn diagram. So this is the A over here, your blue shaded area here. A complement would be the green shaded area, alright? Now what I want to do is, if this is A complement, I want to take the complement of A complement, right? And remember what you mean by taking the complement of this set A complement, right? What you're doing is you want to find all elements in S that do not belong to A complement, right? Okay, and all elements that do not belong to A complement would actually just be the elements belonging to A, right? So that's a justification that A complement is actually equal to A. Alright, some of these you really can justify them by using the definition of say what intersection or union is, right? And the definition of in this case of the empty set, right? So really in order to show these things you need to go back to your definition, right? Okay, so for example, this one here, right? If we consider A intersect the empty set, right? Okay, so A intersect this empty set is going to be some subset of your sample space S, right? And considering this A intersect the empty set, right? Well, what is intersection, right? Intersection would be the event that contains all elements that are common to A and B, right? So intersection of A and B are all elements that are in common with A and B, right? Okay, so if we consider intersection of A with the empty set, right? Well, what you're going to get is you're going to get a subset that consists of all elements in common with A and the empty set, right? But the empty set doesn't contain anything, right? Which means that there's nothing in common between A and the empty set, right? So if you take the intersection of A with the empty set, you're really just going to get back the empty set, right? Right. And this one here, where A union the empty set, right? Well, what is union, right? Union consists of all elements that either belong to A or belong to the empty set, right? So all elements that either belong to A or belong to the empty set. Well, the empty set isn't going to contribute elements. The only elements that you're going to get would be from A, right? So the resultant subset that you're going to get would be just consist of elements that just come from A. And elements, the set of all elements that just come from A is in fact just A itself, right? There's more formal ways to prove this, right? And you're going to see more formal way. For example, I'll prove one of these De Morgan's laws, right? So you'd see a more formal way of proving, right? But that would be a justification for it, right? You can use your definition of union to justify that if you take the union of the empty set with a subset A, you're just going to get back A, right? Let's consider this one, number 5, right? That S complement is equal to the empty set, right? Okay, so what is complement, right? Remember when we take in complements here, we take in complements relative or with respect to uh, a sample space S, right? So this is a set containing all my subsets, right? Okay, so um, when I'm doing my calculations, if I'm just proving these sorts of things, right? I'm assuming that there's some large set S over here that's containing all the subsets that I'm interested in, right? Okay, so if I'm gonna take okay, so this definition here, right? Well, what is complement of A complement of A, right? A complement of A is set of all elements of S that do not belong to A, right? So that's your definition of A complement. Now, what I'm looking at over here is S complement, right? So S complement using this definition, right, means that I'm going to be considering a subset of S that consists of all elements that do not belong to S, right? Okay, but a subset of S that doesn't actually have any elements belonging to S must necessarily be an empty set, right? So that would be how you'd get justify this over here. Right, and if we want to show that this one here, that phi complement is equal to S, right? Empty set complement of the empty set is going to be equal to S. Well, then what I can do in order to show 6 here is I can use 5 and 7, right? Okay, so what I want is phi complement, right? Now phi is actually equal to S complement, which we just justified already. Okay, so I have phi complement, and if the phi is S complement, then what I'm actually doing is I'm taking the complement of S complement, right? Okay, and if I'm taking S and I have complement and I take the complement again, that's just going to be S, right? We showed this already, right? Okay, so what I'm saying here is that in order to show phi complement is equal to S, I really just use statement 5 over here and statement 7, and I combine them to show statement 6. Alright, so let's show one of these De Morgan's laws here, right? So I'll show statement 9 here, right? Okay, so we want to prove this, right? And we're going to prove it somewhat formally, right? This sort of profers outside the scope of this course. I'm doing it for those of you all who may be interested in it, right? Okay, so if you have the idea here is that if I want to show that the set on the left hand side is equal to the set on the right hand side, right? What you do is you first show that the set on the left hand side is a subset of the set on the right hand side, and then conversely, what you do is you show that the set on the right hand side is a subset of the set of on the left hand side, right? And if you have this one is a subset of this and this one is a subset of this one. Right. Okay, so if you have the one on the left hand side is a subset of the one on the right hand side, and the one on the right hand side is a subset of the one on the left hand side, that actually will imply that you have set equality, right? Okay, and that's what is done in this proof over here, right? So you have the A union B complement, which is this left hand side, and then you have A complement intersect B complement, which is this right hand side here, right? They happen to give these names in this proof. They call in P, set P is the left hand side and set Q is the right hand side, right? You don't really need to use P and Q over here, but they do, right? Okay, so how you show that your left hand side is a subset of the right hand side is you pick an arbitrary element on your left hand side, right? Okay, so arbitrary element on your left hand side is an element of A union B complement, right? Okay, so you have an element of A union B complement, right? So if X is an element of A union B complement, it means it's outside over here, right? Okay, so if X is element of A union B complement, it means it's outside over here. So X does not belong to the union of A and B, right? Which means, and this is a key step over here, right? If X doesn't belong to the union of A and B, right, it means that X doesn't belong to A and X doesn't belong to B, right? So you want to be careful over here. This is where the and comes in, right? Okay, and the and will lead to this intersection here, right? So if X doesn't belong to A union B, it means that X does not belong to A and X does not belong to B. Because if you had an O over here, you would allow the possibility that, say, X doesn't belong to A, but X could possibly belong to B, which wouldn't work, right? So what you have is X. If X doesn't belong to A union B, it means that X does not belong to A, and X does not belong to B, right? And then once you go from here to here, really, you're more or less done, right? Because if X doesn't belong to A, that is equivalent to saying that X belongs to A complement, and X doesn't belong to B means that X belongs to B complement, right? And if X belongs to A complement and X belongs to B complement, it means that X belongs to the intersection of A complement and B complement. Okay, so what you just showed is that if I have an arbitrary element X inside here, on the left hand side, it's an element of that it's going to be an element of your right hand side, and that actually shows that your left hand side is a subset of the right hand side, right? And now what you want to do is you want to reverse the directions, right? You take an arbitrary element of your right hand side now, right? So we're calling it Y in this case. So Y does not belong to A complement intersect B complement, right? Okay, so that means that Y belongs, okay, so Y belongs to A complement intersect B complement means that Y belongs to A complement and Y belongs to B complement, right? And now you use your definition of complements. Y does not belong to A and Y does not belong to B, right? Okay, so if Y does not belong to A, right, and Y does not belong to B, right, well, what you say now is that if Y doesn't belong to A and Y doesn't belong to B, it means that Y is outside of the union of A and B, right? So Y does not belong to A union B, so that's how you go from this step to this step, right? Okay, and if Y does not belong to A union B, Y belongs to A union B complement, right? Okay, and what you just showed is that if you have arbitrary element Y belonging to the right hand side, it in fact belongs to your left hand side, right? Which shows that your right hand side is a subset of the left hand side, right? Okay, so we showed that the set on the left hand side is a subset of the set on the right hand side. Set on the right hand side is a subset of the set on the left hand side, and that would in fact justify the set equality, right? So this is your formal way of showing set equality, right? And in fact, right, each of these over here, to prove them formally, you would in fact, if you wanted to prove them formally and you don't want to use Venn diagrams, this would be how you'd do it, right? Okay, but as I said, that's outside the scope of this course, right? This is really, well, I'd expect you to know these identities here, right? And it's a good idea if you have an idea where they come from, but the main thing is that you know these identities and you're able to use them. So let's recall this experiment where we flip a coin 3 times, right, in succession, right? Okay, and we saw that the set of possible outcomes, the sample space, contains 8 elements, right? You can get all heads, head, head, tails, head, tail, heads, so on, right? And you have 8 of these, right? Okay, and how we, well, in this particular case, we actually listed all the elements in the sample space, right? Now, sometimes, or probably most of the times, we don't actually want to list all the elements in the sample space, but we still do want to have an idea of what the size of the sample space is, right? Okay, so how we're going to do that is certain experiments consist of stages, right? So, for example, this experiment here, your first stage was tossing the coin once, right? And then once you completed the first stage and you got an outcome, you had a second stage, right? And for each outcome in your first stage, you have a certain number of possible outcomes for your second stage, right? And then for each outcome in your second stage, you have a certain amount of outcomes for your third stage, right? And you want to notice that the amount of outcomes you have for your third stage doesn't make a difference if on what the outcomes are in your second stage, right? So if I have a head over here, I get 2 possible outcomes here, and if I have a tail over here, I have 2 possible outcomes here, right? Okay, so this is an example of an experiment with several stages, right? In this case, you have 3 stages, right? Okay, and if I wanted to get the size of the sample space over here, I can work with the stages that I have, right? And that is what this multiplication principle is about, right? To start off with, the multiplication principle is defined for 2 stages, right? So I guess we can look at an example of that, right? All right. Okay, so if an experiment consists of 2 successive stages, right? So in this case, if I flip a coin, if I'm flipping a coin twice, right? So this different example consists of tossing a coin now twice, right? And I want to get the size of the sample space, right? Okay, so I'm tossing the coin twice. This is where I start. And when I start, I have after I flip once, I have 2 possible outcomes. And then for each outcome after the first stage, right, I'm gonna have 2 more possible outcomes for my second stage, right? Okay, so that's what's going on over here, right? You have an experiment that consists of 2 successive stages, right? So here, this is an example of a first stage, and here, this is an example of a second stage. The first stage can be performed in n1 distinct ways, right? So if you're starting from here, what this means is that the set of possible outcomes after your first stage is that you have n1 possible outcomes, right? So this is small n with subscript 1 over here, right? And this 1 over here is to indicate that it's first stage. Okay, and then your second stage, it can be performed in n2 distinct ways, right? So what that means is that once you complete your first stage, you get an outcome. Then when you're doing now your second stage, you can have several possible outcomes, right? And the amount of outcomes that you can have for your second stage doesn't depend on the outcomes from your first stage. In other words, if it's a head, you're still going to have 2 possible outcomes for your second stage. Or if it's a tail over here from your first stage, you're going to have 2 possible outcomes here, right? So the number of lines coming here is 2, and the number of lines over here, for example, is 2, right? So it's not, say, 2 over here or 3 over here, right? Anyway, so n1 is, in this case, n1 is 2, right? For your first stage, you have 2 possible outcomes, and n2 in this case, for your second stage, you have 2 possible outcomes here, right? So, and once you have this here, right, the size of your sample space, what you do is the amount of outcomes for your first stage and the amount of outcomes for a single outcome of your second stage, right? This is n2, right? The n2 is 2, right? This size of your sample space once you have a two-stage experiment like this would be the n1 times the n2, right? Okay, so in this case, the n1 is equal to 2. The n2 is equal to 2, right? So size of your sample space would be n1 times n2, which is 2 times 2, which is 4, right? And you see in 4 possible outcomes over here, right? Okay, our next way to look at this intuitively is you have 1 over here, and then for each one over here, you have n2 of these, right? And this one over here, you have n2 of these, but you have n1 of these over here, right? So your total number here is going to be n1 times n2, right? Okay, and so that's if you have a two-stage experiment, right? Now, if you have a three-stage experiment, such as this one over here, right? So if you have more than 2 stages, like this one over here, where you have 3 stages, right? The set of possible, so you have your experiment that consists of tossing a coin 3 times, right? And in this problem, what I want to get is I want to get the size of the sample space, right? They didn't ask me to, in fact, list all the elements in the sample space. They're just asking me to get the size of the sample space, right? And here I have 3 stages, right? First stage 1 has 2 possible outcomes, right? Second stage, once I perform my first stage and I get an outcome, the second stage would have 2 possible outcomes here, so I have 2 here, right? And then if I complete, so the n2 is equal to 2, and if I complete my second stage and I'm looking at a certain outcomes, there's n3 amount of ways to get to the third stage, right? Okay, so there's n1 amount of ways of doing your first stage, n2 amount of ways of doing your second stage, n3 amount of ways of doing your third stage. And the n1, n2, and n3 in this particular case all happen to be equal to 2. Doesn't always have to be like this, right? But in this case, for this problem, the n1, the n2, and the n3 are actually all equal to each other, right? Equal to 2, right? Anyway, so the size of the sample space using your multiplicative property is n1 times n2 times n3, right? So in this case, you have k is equal to 3 stages. So you have n1 times n2 times n3, which is 2 times 2 times 2, which is 8, right? So the size of the sample space is equal to 8, right? Okay, and as I said, the good thing about this is that you get in the size of the sample space without listing out all the elements here, right? Alright, so let's do a next example of this multiplication principle, right? Right, so I have a club with 22 members and I want to elect a chairman and a treasurer, right? And a member cannot hold both posts, right? Okay, so you're going to have a chairman position, you're going to have a treasurer position, right? And a member cannot hold both posts, right? Okay, so you can regard this as being an experiment where you have 2 stages, right? Your first stage is selecting the chairman, and your second stage is selecting the treasurer, right? Okay, so if you're selecting the chairman, right? So let's say we select the chairman first of all, right? Well, then there's 22 ways of selecting the chairman, right? Okay, and then once you select the chairman, you're gonna select the treasurer, right? But a member cannot hold both posts, right? So whoever you chose as the chairman, you can no longer select to be the treasurer, right? So now you have 21 people to choose from, right? Okay, so you have 22. This first stage over here, the amount of ways of completing your first stage is n1 is equal to 22. The second way of the number of ways of completing your second stage is n2 is equal to 21, right? And by a multiplication principle, the set of possible outcomes would be n1 times n2, which would be 22 times 21, which is this 462.